Welcome, everyone. We're here at the University of New South Wales. I'm Norman Wahlberger, and we're carrying on with a sort of overview of abstract algebra in this course on algebraic topology. Today we're going to talk a little bit about free abelian groups, and then say some things about non-commutative groups. So free abelian groups are types of groups that are very closely modeled on the integers. So the integers, of course, form a commutative group. We've already talked about the elements 0, 1, 2, and so on, minus 1, minus 2, and so on. And this group has the property that there are essentially no relations. If you take this number 1, you can add it to itself as many times as you like, and you never get back to a previous element. It's sort of free in some sense. So this is kind of a model of the simplest kind of free abelian or free commutative group. I should maybe point out that there's also a notion of free group, which is different from the notion of a free abelian group. The notion of a free group resides in this non-commutative story. Today we're just talking about free abelian groups or free commutative groups, same thing. So what is a free abelian group? Well, perhaps the simplest way of describing this is to start with a set. So we have a set, say X, and we'll start with a very simple set, say A and B. And we're just going to think of those things as being symbols. And then we're going to create an algebraic structure from those symbols by allowing ourselves to take sums of A's and B's. So that what we do is we consider linear combinations of A and B. And these are just expressions that we write down. For example, NA plus MB, where the N and the M are integers. So we're allowing ourselves integral combinations of A and B, and those are the elements of this free group. So we might say free abelian group on X consists of objects of the form NA plus MB, where N and M are integers. And I have to tell you how to add them, and we do that in sort of the obvious way. So the addition is the obvious one. Let me do it with an example. So if you have 3A plus 4B, that would be one element, and another element might be 2A minus 7B. And if we added them, well, we're going to add the A's to get 5A, and add the B's to get minus 3B. So that's how we add. And then the inverse of an element like NA plus MB is just minus NA minus MB. And I'll write minus MB instead of plus minus 1 MB. And the identity is just 0, 0. 0N, 0A plus 0B. All right, this particular free abelian group is reasonably obviously isomorphic to the integers, direct sum of the integers. And we could make an isomorphism, say phi, from, say, the integers plus the integers to this free abelian group on X by associating or pairing up the pair Mn, pair of integers, to this linear combination Ma plus Nb. Now if we started with a bigger size set than X, then we would have a sort of bigger free abelian group, but the story is pretty well always the same. So the number of elements in X is the rank, called the rank of the free abelian group Fa of X. So in our example, the rank is 2. The point of taking these combinations is, first of all, it connects quite well with linear algebra. So this whole story is very close to being like vector spaces. This theory is a lot like the theory of vector spaces. Because we take combinations and we add just like we add combinations of vectors. And the rank corresponds to a dimension in vector space theory, sort of parallel concepts. It's also possible to consider free abelian groups where the set X is itself infinite. Okay, that's also possible. A little bit more delicate in terms of establishing the foundations of it, but it's still possible to consider that. So if X is infinite, we still consider only finite linear combinations. So Fa of X is, consists of finite linear combinations. And there are sort of two important theorems to, at least to mention, with free abelian groups. One is the fundamental theorem of finitely generated commutative groups. This is an extension of the fundamental theorem of finite commutative groups, where we allow these sort of infinite free groups to enter the picture too. So the story is that a finitely generated commutative group, and finitely generated means that there are a finite number of elements say G1 up to Gn, such that any other element in the group can be expressed by some suitable combination of these guys. So there are a finite number of elements, G1, Gn, so that any x in the group is of the form x equals n1 G1 plus n, maybe I'll use m1 G1 plus m1 mn Gn, mi and z. So if we have such a finitely generated commutative group, G, then G is isomorphic to a certain number of z's. Z, direct sum z, direct sum z. And there might be r of these, together with some, say, h, where h is a finite commutative group. So for example, a typical finitely generated commutative group is isomorphic to perhaps something like Z plus Z plus Z4 plus Z8. Okay. So this thing here is, we know from the fundamental theorem of finite commutative groups that such a thing can be written as a sum of cyclic groups. And so we're kind of extending that to also having these infinite cyclic factors as well. So the rank here would be 2. Rank of G is equal to 2. This is sort of the free part. This is sometimes called the torsion part. Torsion is a word that refers to having finite order. Okay, it means that the elements from this subgroup have the property that their order is finite. Finite order. All right, so that's an extension of the structure theorem for commutative groups to these somewhat more general, or quite a lot more general, finitely generated commutative groups, which allow us also to incorporate these infinite cyclic groups as factors as well. I'll mention 2 more theorems. Another theorem is that any subgroup H of a free abelian group is also free abelian. And in fact, its rank is less than or equal to the rank of G. Fine abelian group G. And another thing, finally, that we need to at least have seen is that there's a kind of a universal property that these free groups have. So, universal property. The universal property is that if we start off with a set X, say if X is a set of elements A1 up to AN, and we have, and G is a commutative group. And then any map function f from X to G extends uniquely to a homomorphism. Let's call it F. From the free abelian group on X into G. Let me illustrate this sort of in a special case, make it a little bit more concrete. So, for example, suppose that we go back to our set X, which is set AB. And let's take G to be, say, Z2 plus Z4. All right, and let's just start off with an arbitrary function, f from x into g. So it's defined by what f of a is and what f of b is. Let's suppose that f of a is the element 1, 2, and f of b is the element, say, 0, 3. These are just two random elements in this group that I've picked. I'm just choosing any old function from the set x into the group. Then the universal property is that if we look at the free abelian group on x, and I remind you, that consists of things of the form ma plus nb, where the m and n's are integers. Then we can extend this function f to a homomorphism. And we do it in sort of an obvious way. We define f on ma plus nb to be m f of a, or m little f of a, I suppose, plus n little f of b. So in other words, m times 1, 2 plus n times 0, 3. And that will then be the pair m and 2m plus 3n. And that's now a homomorphism of groups. It's a homomorphism of groups that just extends this random function from the set x into this group. I'm going to try to draw a picture of that a little bit. So let's draw a picture of that story. So I'm going to try to draw a picture of f of a of x. So a picture of the group whose elements are ma plus nb. And what I'm going to do is I'm just going to think of this as being some two-dimensional lattice like z plus z. I'm just going to take the ordinary plane with the standard integral lattice. And I'm going to think of this point, say, as being A, and this point as being B. And then this will be 2A. This will be 2B here. This will be A plus B. This will be 2A plus B, and so on. So all the integral points on this lattice, also negative ones, correspond to elements in the free group. Okay? So the free group can be pictured as all the dots on this integral lattice in the plane, linear combinations of A and B, and here I'm just putting A and B wherever I want to get some kind of representation of this free group. Now over there, we had this group Z2 plus Z4, and we can visualize that by a similar kind of diagram, a product. So here's going to be a Z2, and here's going to be a Z4. I'll mark that 0, 1, and that 0, 1, 2, 3. Okay. So here's the group Z2 plus Z4 in terms of coordinates. And what did I do to establish this map? Well, I had a map F. And the map F sent A, this point here, to the point 1, 2, which would be 1, 2. So here is f of A. So A got sent to that point, and B was sent to 0, 3. 0, 3 right here. There's f of B. And the typical, I'll just write that down again, the typical point MA plus NB, we decided went to m 2m plus 3n. 2m plus 3n. So that's a homomorphism from this big doubly infinite free group to this very finite group. And when we ever have a homomorphism like that, we should ask, is it onto, and what's its kernel? Well, it's probably not too hard to see that this is going to be onto. Maybe I call this capital F. So F is from the free abelian group on X to our group Z2 plus Z4. This is onto. So every element can be covered of these 8. And what's its kernel? This is interesting. What is the kernel? The kernel consists of those elements here that get sent to the identity element, which is right here. So we have to ask, when is this thing going to be 0 in Z2 plus Z4? Well, the kernel, just look at this. If this is going to be 0, it means that m has got to be 0 mod Z2. So it means that m is even. And if m is even, then this thing here, 2m plus 3n, has to be 0 mod 4. It has to be 0 mod 4. What does that mean? Well, if m is even, then 2m is already 0 mod 4. So it's just the condition that 3n is 0 mod 4, which is the condition that n is a multiple of 4. So n is even, n is a multiple of 4. So the things that get sent to O, the kernel of this map, looks like this. It's all the things here, all the linear combinations, where m is even, m is the coefficient of A, and n, the coefficient of B, is a multiple of 4. There's 3, there's 4. So what does that look like? Well, we can draw it. So there, 2, there's 3a, 4a. So this one, this one, this one, minus 2, and then up 4, up 4, up 4. Right? So we get a big, this is a subgroup. All the yellow ones that I'm marking, and we keep going over 2 in this direction, up 4 in this direction, backwards and forwards. That gives us a subgroup H, or the kernel of F. It's now a subgroup of this infinite free group, and you can see that it's also a free group. The subgroup H is also isomorphic to Z plus Z. We talked about cosets last time. This is probably a good place to have a little bit more practice about cosets. So what do the cosets of this subgroup H in the big group, this free abelian group, look like? What are the cosets? What are the cosets of H, which is the kernel of our transformation, in G, which is our free abelian group X? Well, you can see it very physically here, because the subgroup is just these lattice points spaced 2 and 4 in this direction. And a coset is just what you get when you translate that whole grid pattern in any direction. Okay? So for example, if we translated once to the right, then we would get this point here. Well, I'll mark a coset. So here's a coset. That one, that one, that one, together with that one, that one, that one, and then similarly, spaced out. That would be one coset. Another coset would be, say, this one here. Over 2, over 2, up 1, up 1, up 1. It's another coset. And what do the set of all cosets look like? Well, the set of all cosets is parameterized by the points just in this region right here. Every coset is going to meet this representative area in exactly one point. And so the cosets themselves as a group form something that's exactly like Z2 plus Z4. And that's a typical situation that what happens is that the group G divided by the kernel of this map F is isomorphic to the image of F. So in this case, this is Z2 plus Z4. This is our free abelian group on A and B. And this was this kernel that's generated by the relations 2A and 4B. Really the free abelian group on 2A and 4B. All right, very good. So that's a brief little intro or overview of some aspects of free commutative or free abelian groups. Now I should say a little bit about non-commutative groups. The story for non-commutative groups is much harder than for commutative groups. It's orders of magnitude harder. It's at least 1,000 times harder. So when one studies group theory, one really ought to study the commutative situation first, in my opinion, which is much, much simpler. So the non-commutative situation is also, of course, pretty interesting, but a lot harder. All right, we're not going to use any deep facts of non-commutative group theory. It's a vast subject, very, very interesting. Most of the things that we're going to be using are going to be very simple-minded. We've already talked about fundamental groups a little bit in this course, and they were often examples of non-commutative groups. So the examples that come up in algebraic topology are often pretty close to related to fundamental group of a surface or of a space, which are generally non-commutative, but they can be also commutative. All right, so I'm not going to go over the whole theory. So let's make sure that we all understand what the definition is. So the definition is that we have a group, we have an operation. The main operations are still satisfied, so we still require that associativity. We require the existence of an identity. That's the identity E. And we require the existence of inverses. So given any element A, there's an element B, so that A times B equals B times A equals E. Okay. The crucial thing that we don't require is the commutative law, that A times B is B times A. We don't require that. Okay. It is missing, which makes things a lot harder in the sense that we have to be more careful about the order of elements that we use. But most of the definitions that I talked to you about in the commutative setting still apply in the non-commutative setting. We still have notions of homomorphism, which are exactly the same, of isomorphism, which are exactly the same, subgroups are exactly the same. Cosets are somewhat different. Cosets and quotient groups are different. The story becomes more subtle when we get to quotients and cosets. What about examples? Where do commutative groups come from outside of algebraic topology? Well, the easiest way of getting a group generally is to use transformations. The reason is that it's this associative law here that's hardest to satisfy, hardest to check. Okay? Because you need to have this law satisfied for any A, B, and C in the group. And if you just have a big group table or something, that can be a lot of hard work. So the easiest way of making sure that associativity is sort of automatic or easy to check is to consider groups of transformations. Associativity is easiest to check with groups of transformations. That means we have some space X, and we're considering functions from F from X to X. Okay? If the functions are invertible, and we want them to be invertible because we want there to be inverses, then if we have one function f and another function g and another function h, we have some element x, and we first perform f, and then we perform g, and then we perform h, so h of g of f of x. Then this composite of three things doesn't depend on whether we decide to group f and g together or whether we decide to group g and f together. So it'll be automatically the case that transformations satisfy the associative property. And so that's why when we're looking for examples of groups, we like to look at groups of transformations of some object, and also why groups of matrices are important, because the simplest transformations are linear transformations. So the most important group is almost surely GLN. Okay. This is the group of n by n invertible matrices. And I remind you that the matrix M is invertible precisely when its determinant is non-zero. So this is a group. GLN is a group. If it's invertible, it means that there's an inverse. The identity element is the usual identity matrix. And multiplication, the operation is matrix multiplication. That's the number one example of a group. Number two example, which is closely related to that one, is a symmetric group. Number two example is the symmetric group. Sn, which has different incarnations, and there's different ways of thinking about it. In terms of matrices, we can think about this as being consisting of permutation matrices. Those are matrices that are zero in most of the elements are zero, except there's a few ones, and there should be exactly 1 1 in every row and column. Okay, so these are 0, 1 matrices with exactly 1 I might write 1, 1 in each row and column. That's one way of thinking about what the permutation matrices are, one way of thinking about what the symmetric group is. And I suppose the standard example is always S3. So let's have a look at that, because that's the simplest, smallest non-commutative group. So let's have a look at S3. S3 consists of 3 by 3 matrices. And let's write them down, permutation matrices. So there's that one, and then there's this one, and then there's that one. There's 3 of them. Okay, and then there's another one. Like that. And then there's also, all right, so those are the 3 factorial or 6 different permutation matrices, and you can multiply them together, and you'll see that the product of any 2 of them is another one. But it's a non-commutative group. That's easy to check. If you multiply this times this, probably get something different from this times this. In fact, you will. Now, it's a little bit onerous to write these 3 by 3 matrices all the time, so we want more efficient ways of encoding permutations, and there's a number of ways of doing that. So let's choose one of them. Let's say this one here. So if we look at this matrix, one way of thinking about what it's doing is to act on a vector, x, y, z. If we think of it as acting on a vector, then x, y, z is sent to do the multiplication, z, x, y. Okay. So what we see is that the three coordinates have been permuted, and if we want to record that permutation of just the coordinates, we could say, well, at the first, here are the positions of x, y, and z, that the thing that was in the first position has gone to the second position. So one way of recording that would be like this. The thing that was in the second position has gone to the third position, and the thing that's in the third position has gone to the first position. So that would be another way of recording the permutation. And often that's done without the arrows, so just one line with another line below it. Another way of describing that is using cycle notation, where this is the most efficient way of representing things. You start with, you think of these 3 elements, 1, 2, and 3, corresponding to the 3 positions. And you say, all right, let's look at the thing that's in the first position. The thing that's in the first position goes to the second position, so we'll follow the 1 by a 2, telling us that the thing that's in the first position has gone to the second position. On the other hand, the thing that was in the second position has gone to the third position, so we would write a 3. And the thing that was in the third position has gone to the first position. Well, we don't want to write a 1 again. We'll just close this thing off, and that means that the thing that the thing that was in the third goes back to the first position. So this is cycle notation for this particular matrix. So let's look at the cycle notation for these things. This is the identity. This one here permutes 1 and 2. This one permutes 1 and 3. This one permutes 2 and 3. This one we've decided was permutation 1, 2, 3. What about this one? Well, if we start with 1, if you multiply it with x, y, z, you'll see that you get y, z, x. So the thing that was in the first position goes to the third position. The thing that was in the third position goes to the second position. And the thing that goes in the second position goes back to the first position. So this is the cycle structure for this group. And now we can write down a multiplication table. And the table will have 36 entries because it's a 6 by 6 table. So E12, 13, 23, say 123, 132. E12, 13, 23, 123, 132. And here's our multiplication. And let's agree that when we multiply, for example, 1, 3 times 2, 3, what's this going to mean? That means the corresponding matrices multiplied together. Okay? Or in other words, in terms of the action on the vector, we're going to do this one first and this one second. That's just a convention. We don't have to do that. We could do it the other way around, but it sort of corresponds to matrix multiplication if we want to think of these things as matrices. Okay, we could do this. It's a little bit of work, but not too much. The identity, of course, acts as it should. These guys are transpositions, so when we multiply them by themselves, we'll get back the identity. 1, 2 times 1, 3. Let's calculate that. 1, 2, 1, 3. So to calculate that, we're going to do this one first and this one second. So here's how we do that. We're going to get a new cycle. And what we're interested in is writing down immediately what that cycle is. So we'll start with 1 and ask, where does 1 go? So we're doing this one first. The thing that was in the first position goes to the third position when we apply this. That's what this is telling us. So we started with something in the first position. Now it's in the third position. We're following it. And then when we do this, what happens to it? Well, this only interchanges the things that are in the first and second position. So the thing in the third position stays where it is. So that's where the thing in the first position goes. Now we have to figure out what happens to the thing that was in the third position to begin with. When we apply this one, the thing in the third position goes to the first position. And then when we apply this one, the thing that's in the first position goes to the second position. So altogether, the thing that's in the third has gone to the second. And just to check what happens to the thing that was in the second position, here it's not moved, and here it's sent to 1. So it closes up, and we get 1, 3, 2. So I've just calculated 1, 2 times 1, 3. It's 1, 3, 2. All right, so it was an excellent exercise to complete this table. And then we can ask, well, what about the subgroups? What are the subgroups of this thing? Well, of course, the identity is always a subgroup. And the group itself is always a subgroup. And this multiplication here shows that E together with 1, 2 is a little closed subgroup. So we have E together with 1, 2, that's a subgroup. And E together with 1, 3, it's another subgroup. And E together with 2, 3, similarly. These are subgroups with 2 elements. And are there any other ones? Well, there's also one more subgroup. E with 1, 2, 3, and 1, 3, 2. Let me just clarify what the multiplication there is. So 1, 2, 3 times 1, 2, 3. If you do that twice, you get 1, 3, 2. And this one times this one will be E, E, and 1, 2, 3. So this is a little subgroup as well. famous theorem of Lagrange tells us that the order, if H is a subgroup of G, then the order of H always divides the order of G. So it's impossible for a group of order 6 like this to have subgroups of size 4 or 5. Well, what about cosets and multiplying cosets? Already we can see the interesting aspects in this very small group. The two kinds of non-trivial subgroups that we're finding here, these subgroups of order 2 and the subgroup of order 3, act quite differently. Okay? This one is a normal subgroup. It's a normal subgroup. Well, what that means is that it means that its left cosets and its right cosets are the same. If you have a group like these ones here, these are non-normal subgroups, these three here. Well, when we looked at the subgroup of a commutative group, we said we should look at cosets of it when we translate the subgroup by an element to get a coset. You can do that here, but the trouble is you can translate on the left or on the right, and it matters which one you do. Translating by an element on the left is different from translating by an element on the right. So just to illustrate that, let's take one of those cosets. Let's call it K. This subgroup, rather, E12. Let's look at that subgroup. And let's look at its translate by, say, 1, 3. If we translate it on the left, we're obliged to take 1, 3 times E, which is 1, 3, and 1, 3 times 1, 2, which is 1, 3, together with, this one here is, did we calculate that? No, we calculated the other one. 1 goes to 2, which stays where it is, and then 2 goes to 3. So that's a coset of this subgroup. That's actually a left coset, because we've multiplied the group by something on the left. If we look at K times 1, 3, then we're obliged to multiply all of these elements by 1, 3 on the right. We get something possibly different. We're going to get 1, 3 still, but now we're going to get 1, 2 times 1, 3 on the right. And that is 1, 3, together with the element 1, 3, 2. That's a right coset. So the story that we get is that we get a subdivision. G subdivides, or is partitioned, by the left cosets. So for example, if there's G, then there might be K, and there's A, K, and there's B, K, and there's C, K. Or by the right cosets. In which case the picture would be K is still looking the same, but now A sub K might look like, or K sub A might look like this, and K sub B might look like this, and K sub C might look like this, roughly. So we have two different subdivisions or partitions of the group into cosets, into either left cosets or right cosets. And when that happens, the cosets themselves do not form a group. Okay? We cannot multiply these cosets consistently to get a group. So no quotient structure, no quotient group structure in this case. But in the normal case, when we're like that subgroup H, then the cosets that are the left cosets and the right cosets, they agree, then the situation is much happier, and then we do get a quotient group. All right, so that's been a fast and furious introduction to non-commutative groups. Very good exercise to work out S3 and play around with all the cosets of these various subgroups and see how they fit together. See you.